Good morning, and welcome to the first virtual CRISP Partners meeting. I'm John Thompson, the Catskill Regional Invasive Species Partnership Coordinator, and I'll be hosting this update and webinar today. Our featured speaker will be Dr. Andrew Reinmann, and I'll introduce him in a few minutes to discuss a project that he is working on to use remote sensing to map hemlock stands and monitor hemlock health. If you hover over the lower part of your screen, you can click on the chat box. Please say hello in the chat box and let us know where you're from. I would like to begin this webinar by providing an introduction to the Catskill Regional Invasive Species Partnership, CRISP. But first, I'd just like to say thank you for joining us. And our hearts go out to all of you that are facing difficulties in these uncertain times. And we wish you the best of health and safety, and hope that we can be a resource for you going forward. At CRISP, we promote education, prevention, early detection, and control of invasive species to limit their impact on the ecosystems and economies of the Catskills. And we work over an area that includes 7 counties. We include all of Otsego County, all of Schoharie, all of Delaware, most of Greene, most of Ulster, and most of Sullivan County, and a small part of Orange County. CRISP covers over 3.3 million acres. In 2020, through our request for proposals and our request for bids, we chose to fund all of these projects on this slide. They include SUNY Oneonta for the CRISP Watershed Stewards Program, Canadarago Lake Improvement Association for the Watershed Stewards Program, Otsego Land Trust for Aquatic Invasive Species Outreach, Otsego County Conservation Association for Aquatic Invasive Species and Japanese Angelica Tree Rapid Response, Buck Environmental Solutions for Rapid Response for Mile-a-Minute Japanese Angelica Tree, Black Jetbead, and Japanese Tree Lilac, Mountaintop Arboretum for Lesser Celandine Rapid Response, Cornell Cooperative Extension Sullivan for Spotted Lanternfly Trainings, Cornell Cooperative Extension for their CRISP Network of Education and Outreach, and the Ecological Research Institute, which does our monitoring and managing ash or MAMA project. All of these are great projects, and we would look forward to working with you this year. For the presentation today, please ask any questions in the chat box, and I'll read them to Andy for his response. After the presentation, I'll provide some CRISP and partner updates and upcoming events. It is my pleasure to introduce our featured speaker today, Dr. Andy Reinmann. Dr. Reinmann is an ecologist and biogeochemist who focuses on plant ecophysiology and the terrestrial carbon cycle. He is particularly interested in understanding the effects of environmental change, for example, climate change, urbanization, and land cover change, on the drivers of plant-mediated controls of terrestrial carbon cycling across a continuum of human-disturbed ecosystems. He also works with a variety of stakeholders to better understand how trees and green spaces can be used to mitigate environmental problems such as the urban heat island effect. His research draws from multiple disciplines and combines field observations, ecosystem experiments, and laboratory analyses with GIS, remote sensing, and modeling. Reinmann currently has projects in forested and human-dominated landscapes throughout the mid-Atlantic and northeastern US. We're very excited about the work that Andy is doing with his student, Kelsey Parker, the Catskill Science Collaborative Fellow. And today, Andy will present Mapping Invasive Species Across the Forests of New York, a View from Space. Thank you for joining us, Andy. You have control.
Good morning, everyone. Thank you for taking the time to come and watch my presentation today. I'm going to talk about a couple of new projects that we're getting going in my lab at CUNY, and much of this work is the focus of my PhD student, Kelsey Parker's dissertation work. Unfortunately, for scheduling reasons, she could not join us today, but you have me in her place. And so this work is really focused on leveraging a variety of different freely available remote sensing products like those from Landsat to sort of map the temporal and spatial dimensions of invasive species across forests in New York, specifically those in the Catskill region and DEC regions 2 and 3, excuse me, in the lower Hudson Valley. And this work that I'm going to talk about is largely funded through the Catskill Research Fellowship Program, as well as the Department of Environmental Conservation Invasive Species Program. So before I jump into that work, I thought it would be useful to just give you a little bit of an idea of what my background is, so you have a better understanding sort of the place where I come from when I think about issues related to invasive species. So for the last 10 or 15 years or so, I've been doing a lot of work to try and better understand how different aspects of global environmental change, like urbanization, land cover change, forest fragmentation, and climate change, are altering the way sort of forests grow and function, and more broadly, the impacts of these different aspects of environmental change on the terrestrial carbon cycle. And my interests in the carbon cycle are sort of have a few different prongs to it. Of course, we're all familiar with the important role that carbon and carbon dioxide plays in anthropogenic climate change, and forest ecosystems in particular are capable of offsetting somewhere between 1/4 and 1/3 of all of anthropogenic CO2 emissions. So they play a really important role in helping to mitigate climate change and slow its progression. But I also think of the carbon cycle in forests, kind of a broader barometer of different aspects of ecosystem health, right? So carbon cycling provides us with information about rates of photosynthesis, which have close linkages to different aspects of forest health. It provides us with information about maybe microbial dynamics in the soil, which imparts information about rates of decomposition and changes in nutrient availability and things along those lines. And so being able to measure these things and maybe monitor them over time and across space, for me, I think imparts a lot of information about just how our ecosystems are functioning. And so my background is sort of largely as a field ecologist. And so, you know, historically, I say historically, I'm not maybe super old in 15 years now. But so a lot of my work has used dendroecology, collecting tree cores to better understand tree and forest growth dynamics. We look at different forms of ecophysiology. We look at soil properties. We measure greenhouse gas fluxes in ecosystems. And we make a variety of other forest measurements to understand how our forest ecosystems are functioning. And other research typically involve collecting samples in the field that we'll process in the lab. This may be to look at different aspects of plant and soil chemistry. And then in more recent years, I've become increasingly interested in utilizing image analysis, so different forms of remote sensing tools, as well as GIS analyses and different types of modeling to really help to better understand maybe how some of these plot level measurements that we typically make as field ecologists can be used to better understand landscape scale processes and maybe better understand changes in processes over time. And so my background is not really in remote sensing, but over the last few years, myself and my colleagues, we've started integrating remote sensing more and more into the research that we do. And so some of the broad questions that we try to answer include things like how might forest ecosystem processes respond to projected changes in climate. We have a variety of different ways of doing this. I've been working on a handful of different climate manipulation experiments. These are largely located at Harvard Forest in Massachusetts and Hubbard Brook Experimental Forest in New Hampshire. These are drought experiments. So this is the drought net experiment here on the top left. We have another experiment where we sort of warm the soils of forest ecosystems during the growing season, and then in an effort to try and mimic changes that occur with a declining snowpack, we do some shoveling of snow during the winter. And then we've also done a series of kind of what we call snowpack manipulation experiments, which is really just kind of a dorky, sciencey way of saying that underpaid graduate students go out into the forest with a shovel when it snows and remove the snow to sort of mimic that aspect of changes in climate. And then more recently, I've been at CUNY now for a couple of years, and we're starting to set up some observational experiments at Black Rock Forest in the Hudson Highlands. And I have a student now who's sort of taking advantage of natural gradients and soil moisture between mesic valleys and dry ridgetops to better understand how trees in our forests respond to water stress. But some of this experimental work, what we've been finding from it is that projected changes in snowpack across much of northern New England, as well as in the Catskills, it will result in higher frequencies and severity of soil freezing, which in turn can reduce tree growth. This is especially true for sugar maple trees. We also find that growing season warming in forest ecosystems seems to stimulate tree growth and rates of soil respiration, but that warming, when in conjunction with declines in snowpack and increases in soil freezing in the winter, seems to offset any of these sort of stimulatory effects of warming. And then through some of our precipitation manipulation experiments, we're finding that, among other things, even just sort of short-term extreme droughts can have large effects on rates of soil respiration, so microbial and root activity in the soil. Another big question that we try to answer is how forest ecosystem processes might vary across intact, fragmented, and urban landscapes. And so I use this figure to sort of show this kind of continuum of the different sorts of landscapes that we work in. And I should note that those two images on top there, those are the sorts of places where ecologists have historically gone to understand forest ecosystem processes, how they function, how carbon cycles. But really more and more of our landscape is looking like the two images you see in the bottom. And some of our work shows for that the northeastern quarter of the US, about 25% of all of the forest area is actually within 30 meters of an edge. So this winds up being vastly different than these interior forests that we're used to studying. I've been really interested in trying to figure out, to what extent do forests in these more fragmented and urban systems function differently than the intact forests that we've historically studied. And what we've been finding in this context is that these forest patches or forest fragments that have a lot of edges associated with them, they tend to be more productive per unit area than our intact interior rural forests. But also creating these forest edges growth more sensitive to heat. And some of our most recent work is showing that urban forests might actually be more sensitive to heat than our rural forests. And then, so the most recent addition to our research interests are invasive species. And maybe some of this centers around now being located in New York City, and we have no shortage of invasive species around. But even in rural areas, we find invasive species like hemlock woolly adelgid, gypsy moth, and emerald ash borer. And so it seems really different to separate invasive species from other ecosystem processes. And so over the last year, we've been starting to write some proposals and start up some projects to better understand these dynamics. And in doing this and in working with a lot of practitioners, what we find, and maybe this is true for many of you as well, is that a lot of the organizations and agencies that are charged with managing invasive species and managing forests expend a huge amount of resources just sort of figuring out where these things are and how their populations or their impacts on forests are changing over time. And so what we've been trying to set out to do is start to think about where are there kind of low-cost options to at least get like a fairly good first approximation of the distribution of certain invasive species and how they're changing over time, in hopes that with these sorts of products available, that maybe any group with some sort of GIS expertise available to them could maybe start doing some of their detection of where these species are using these freely or low-cost remote sensing approaches, which would then free up more resources for the management end. And so to work on this project, Kelsey Parker, who is a new PhD student in my lab at CUNY, she joined the lab this past fall, and she's really hit the ground running, and she sort of taking the lead on a lot of this invasive species work. And she helped provide a lot of the data and images I'm going to show you today. She, unfortunately, because of classes, couldn't take part in this presentation. But just to sort of introduce her, she's got a BS from Pace University, and she's always been super ambitious. She did a Fulbright in Zambia before coming to CUNY, and there she was studying soil contaminants and different sorts of heavy metals. So now the two projects that we recently got funded to study invasive species in New York are, the first is a project funded by the DEC Invasive Species Program, and the title of this project is Mapping the Spatio-Temporal Patterns in Invasive Tree, Insect, and Pathogen Occurrences in the Lower Hudson Valley and New York City. And there's sort of two components to this work. The first, as I alluded to earlier, is to develop a low-cost approach for mapping the distribution of invasive species over time. And some of the species that we're thinking about are Norway maple, black locust, hemlock woolly adelgid, possibly oak wilt. There aren't too many, fortunately, there aren't too many cases of these, but we're hoping to take advantage of a few of the places where this does exist, as well as some simulation experiments at Black Rock Forest to figure out if we can detect this with satellite, as well as a suite of other invasive species, maybe also things like ailanthus. And so that's sort of this remote sensing part of it. And then there's a field piece, which is to kind of try and identify impacts of different invasive earthworm species. So as many of you know, the earthworms that exist in New York are invasive. Our native ones were pushed away during previous glaciations. And so now we have European and Asian earthworms. They have different sort of feeding habits. They seem to occupy different niches in the forest floor and soil components of the ecosystem. And so we're interested in looking at how these earthworms might change these ecosystems, and also thinking about what are the feedbacks between earthworms and tree composition. So there's been some earlier work that suggests that impacts of earthworms on the composition of the forest floor, so the amount of leaf litter, and also even mycorrhizal abundance in the soil, can have really important impacts on the different tree species that can regenerate there. So we want to further explore those dynamics in that direction. But then also on the flip side of that is, if you have a forest that's been established by non-native tree species, are there then additional feedbacks to maybe changes in soil properties and soil chemistry that can facilitate establishment of earthworms in those systems? So those are the sorts of questions we're gonna try and seek to answer. And this is going to be focused on a couple of parks in New York City. And we're also going to try and start exploring perhaps different ways that we might be able to quantify or map the distribution of earthworms based on essentially differences in color of the forest floor that seems to exist with and without leaf litter. So now that's sort of in the discussion stages. We haven't tried to work that out yet, but that's sort of where our minds are going. And so this project focuses on the DEC regions 2 and 3. And our other project, which recently got funded by the Catskills Science Collaborative and the Carey Institute, is focused on mapping and monitoring the distribution of hemlock woolly adelgid and related hemlock decline in the Catskill Mountain region of New York, also using freely available multispectral satellite remote sensing. So you see the common theme there. And so this project, we're focusing on areas sort of within the blue line of the Catskills, but then we hope to sort of bridge that geographical extent with the other work that we're doing in regions 2 and 3 in New York. So the question is this funded by DEC, EPF? Sorry, I don't know what the EPF acronym is. If this is about the project in the Catskills, that was money from the DEC that was given to the Carey Institute to issue subcontracts to. or subawards too, which is what we got to work on this project. Oh, I see.
Okay.
Yeah, I think that this funding is from the DEC, given to the Carey Institute, and then subawarded to different organizations like us. And so we're working with the Catskills Science Collaborative on this.
Yeah, and the Carey Institute money does come from the EPF.
Oh, it does. Okay.
Yeah.
That's good to know. Sorry, I didn't trace those funding sources back far enough, but thanks for clarifying. Okay, so how do we go about mapping invasive species with a satellite that is, tens of thousands of miles up in orbit? So here's some examples of what the impacts of different invasive species, what the impacts are in the canopy. So on the top left, there's gypsy moth. On the top right is hemlock decline from the woolly adelgid. And the bottom image is oak wilt. And so you'll notice that the common theme among all of these changes is a loss in foliage and a loss in greenness of the canopy. So there's an actual change in the color of the canopy, and these are the things that we think that we can detect remotely. In addition to that, invasive trees, many of them have a different leaf phenology from our native trees. So here, this image, I'll show it again in a minute, is a native sugar maple on the left and a nori maple on the right. And you can see the pretty stark differences in the leaf phenology of these species. So I was just noticing a question: why focus on satellites and not drones, which would provide higher resolution data? That's true, and that's a great question. The only issue, well, there's a couple of issues with drones. While the data that you retrieve will be superior to what you get with satellites, you can't go back in time with those data sets. You can only start now and move forward. Second, trying to map large spatial extents using that approach can be really, really expensive. And also, there are limitations to places where you can fly drones. You can do this with an airplane, as I'll talk about in a minute, but there's also these limitations with cost and then how frequently you can redo this. So what we're proposing here is not necessarily to take the place of these other approaches. It's rather to provide a low-cost way of getting fairly high resolution data that can span a much larger temporal range than really what's possible using any of these other approaches. So I'm not arguing that this is in place of or better than using airborne remote sensing or drones. Just the spatial and temporal extent of the data that you can collect is really difficult to match using those other sort of flight-based approaches. Okay. So how do we do this? So at its core, we're really trying to pick up differences in foliage or the timing of leaf out or leaf drop. And so one example of how remote sensing scientists go about quantifying this is using an index called the Normalized Difference Vegetation Index. And there's other examples that are sort of looking at similar things. I'm showing this one here just because it's quite common. And so the theory behind it is that green leaves absorb red and blue light for photosynthesis. And so if you calculate the difference between the near infrared light, which the leaves aren't really absorbing as much, they're reflecting a lot of it, the difference between that and the red light, which the leaves are absorbing a lot of for photosynthesis, and you look at the ratio between that difference and the sum of the two, you can then use that as an index for sort of how much green foliage exists within a pixel where you're collecting the image. And so there's an example of this on the left, where the cartoon on the far left is green foliage in the peak of the growing season, and you can see that there's very little of the visible red light being reflected. By comparison, as you get to senescence, there's a much higher proportion of the visible red light being reflected. And so we can use those ratios to understand changes in in leaf cover, and even things related to chlorophyll content over space and over time. And just to give you an idea of how this pans out over the course of a growing season, you can see this ramp up in NDVI from the early part of the growing season to the peak growing season, and then that drops off again as the leaves begin to senesce, and then, of course, the trees without the leaves have the lowest values. And we can sort of collect the same data and better understand sort of where you have dead or declining trees in addition to just that seasonality using this approach. What if the leaves are yellow? Can't the lack of greenness be detected? Yeah, so it's that the lack, we're not actually quantifying green, we're quantifying the wavelengths that are getting absorbed by essentially chlorophyll. And so there's another index called Enhanced Vegetation Index, which is pretty similar to NDVI, but it also incorporates blue light into that. So so we're essentially quantifying the presence or lack of presence of chlorophyll, which is, from the way we look at it, a difference in greenness. So I hope, Sean, that answers your question. Okay, so the satellite that we are going to primarily work with is Landsat. This is NASA's satellite, and one of the, there's a few reasons that we use this. First, the data from it's free. There's data going back to 1984, which means that we have this huge time frame to work with to look at how maybe distribution of invasive species have changed over time and what their impacts are on ecosystems, how that has changed over time. They pass over any particular point every 16 days. So there's fairly frequent passes, enough so that we can look at seasonal changes and we can certainly quantify changes between years. And their spatial resolution is fairly high. It's 30 meters, which is, figure one large tree in the canopy, depending on the species, is maybe 10 meters or so across. So it's a handful of trees within a pixel that you're looking at. And there's this is certainly not as fine resolution as you would get using a drone or an airplane mounted sensor, but from a freely available product, it's about as fine resolution as we have right now. There's some products from the European Space Agency that are at 10 or 20 meter resolution, but they only go back a few years at this point. So we're focusing on the Landsat data. And this image on the right just gives you an idea, sort of a snapshot of the US and how NDVI varies across the country. And it's essentially based on density of vegetation cover. So not surprisingly, these areas like where we are in the northeastern US have the darkest green. This is during the summer. There's the darkest green. This is when all of our leaves are out. And if you contrast that to areas in the Great Plains where it's tall grass prairie, the green is lighter. And then once you go to the arid Intermountain West, it starts to approach zero because there's very little vegetation out there. And you can see some water bodies are showing up sort of in the negative values. These insets on the bottom show the same measurements using two different remote sensing products. Landsat on the left has a finer spatial resolution than the satellite imagery they're showing on the right. Okay, so as a first example, for trying to quantify where we have fairly high levels of invasive tree species, as I mentioned earlier, we're planning to use differences in leaf-on or leaf-off phenology. So asking about resampling to 15 meters. We haven't tried this yet. I should point out that we are about 3 or 4 weeks into this project. So we still have a lot of work that we're doing and a lot of things to think about. And the other thing I didn't mention is we're also going to use worldview imagery, which will give you 1 meter or sub-meter spatial resolution, and also daily passes, only going back a couple of years. But we're going to compare the type of information we can get from Worldview, which is really fine spatial resolution, to what we can get with a freely available product like Landsat that's a little bit coarser, but again, it's free. And there's also a much longer data set. So we are going to start to get at sort of different spatial resolutions and what sort of additional information that gives you. But yeah, thanks for bringing that up. That's a great question. Okay, so here is probably one of the clearest examples of how differences in phenology can be manifested in terms of greenness. And then on the right here, a colleague of mine from Boston University a few years ago developed an approach using Enhanced Vegetation Index, which is similar to NDVI, to quantify the seasonal patterns of essentially greenness in forest ecosystems. And so that's what you're seeing here. These green dots represent sort of that spring vernal window, and the red indicates the autumn senescence period. And you can fit a line to that, and then using sort of the slope of that line, you can quantify what's called the start of spring date. So it's sort of like the midpoint between bud break and full leaf expansion. And we know that there are these differences between invasive species and native species. And to give you an example of what that looks like using remote sensing, here's a picture from a forest patch just north of Boston that I was working on for another project a few years ago, and just happened to notice that half of this forest was a native oak forest, and the other half was was dominated by Norway maple trees. And so my colleague Eli, whose work I just talked about, he ran his algorithm for this section, and you can make out quite clearly where you have the forest that's dominated by Norway maple trees versus where you have the forest that's dominated by native oak trees. There's about a 15-day difference or so in the timing of leaf out between those two forests. And so here, there's no difference in sort of the climate conditions. Really what's driving those differences in phenology is the tree species. So we're hoping to sort of use this sort of thinking and these sorts of analyses at a larger spatial scale to try and pick out where these species might exist. Similarly, we can look at the later phenology of Tree of Heaven to figure out where they are. Okay, so now I'm just going to spend the last few minutes talking about the project that we're going to work on in the Catskills. So like I said, we're going to largely focus on what's inside the blue line. If we have the time, we can extend everything beyond that. But what's inside the blue line is sort of on the cusp of regions 3 and 4. And so we're going to use the project that we're working on that I just talked about that focuses on 2 and 3, as well as this project to sort of bridge those spatial extents. So the first thing we need to do is figure out where there are coniferous forests. And so to do this, we can look at essentially the annual amplitude in greenness of a particular pixel. And here again, I'm showing some of the work that my colleague Eli at Boston University worked out, where on the left here, you can see sort of I think this was an early spring image of a section of Harvard Forest in central Massachusetts. You can very clearly make out where the conifer forests are and where the deciduous forests are. And then on the right is a map of the annual amplitude of EVI. And you can see in these dark blues and lighter blues that very closely corresponds to the forests that are dominated by conifers, where you'd expect there to be very little change over the course of the year, essentially in the amount of greenness, especially in comparison to our deciduous forest, which is in the bright red over here. And then of course, as you shift your forest from pure conifers to pure deciduous, they will go essentially from the darker blues to lighter blues to yellows and to red. And so that's the same approach that we're going to take for the Catskill region. And so I should point out that there has been work to assess hemlock abundance in the Catskills using remote sensing. And this was work that Jennifer Pontius and Rich Hallett, who's actually a colleague of mine who's working on some of these other these other invasive species projects with me, they did this sort of work using avarice about, was it 15 years ago or so now. And avarice is a hyperspectral remote sensing instrument that is flown via an airplane. And avarice has superior spectral and spatial resolution. Like what we have with Landsat can't match that. But as I mentioned earlier, there's limited spatial extent and temporal resolution because of the cost of flying these missions. And so again, what we're proposing is to not replace these missions, but sort of as an addition to these great data sets that allows us to broaden the spatial and temporal extent. So there's a question about IDing hemlocks versus white pine. Yeah, so that's going to be tricky. And then also in the Catskills, we have to think about spruce and fir forests. So by using things like topography and things and elevation, we can tease apart some of this, but without a doubt, there's going to be cases where we're going to just have to label something as conifer and not know for certain if it's a white pine or a hemlock stand. And that's just sort of the nature of remote sensing. There might be some other spectral information that we can look at to help to tease those apart, but we'll have to kind of see how that goes. Certainly with higher resolution and hyperspectral data, we can do that. It's not clear if we can do that using Landsat. Oh, overlaying porcupine population over the hemlock. No, that's a good idea. These are all great. So one of my hopes for this presentation is to have a little bit of a discussion when I finish up here in a few minutes about these sorts of ideas and maybe other things that we're not thinking about or ways that we can make this sort of work more useful to the broader community that we hope will use it. So this work with avarice was done in the early 2000s, but in the 90s, there was some work done to use Landsat to monitor hemlock forest health in New Jersey. And they just did this for 2 time slices. And they use a different vegetation index, but it's pretty similar to what we're proposing to do. And this group in the 90s, what they found is their field plots that they had categorized as having different levels of decline from the hemlock woolly adelgid. There's a really good correlation with their vegetative index. And then they have this really nice image there that sort of highlights this. So the image on the left is from 1984, before the outbreak of hemlock woolly adelgid in this region. And the bright red here is pointing to the healthy stand of hemlocks. The image on the right is 10 years later in 94, and you can see a section of those hemlocks have severely declined, or in the black that indicates that they're dead. So this is a good example, a sort of proof of concept that we can use these approaches to start to map decline in hemlock trees. Yeah, so Leslie's pointing out we can roughly sort conifers by known elevations. I think to some extent that's true. Like we know there's an upper limit to where hemlock's going to live, and probably a lower limit for where we can expect to find spruce fir forest. So yeah, we can separate it out that way. And the abundance of hemlock forest is probably going to be a lot higher than the abundance of like pure white pine forest. So there are some assumptions that we can make here to help constrain our estimates or certainty of where we think these hemlock forests are. So now here's some like very early data that Kelsey's been putting together for the Catskills using the approach that she's developing. And I should point out that this is all very preliminary. Like, this is stuff that she really just started throwing together over the past 2 weeks, while also taking classes and figuring out how to do research and take classes and being a student in this like COVID era where everything needs to happen remotely. But she's making a lot of really wonderful progress. So in these panels, what you're seeing is spatial variations in NDVI. And we expect there to be some variation between years. There's just better and worse growing conditions. And so that is manifested in sort of different levels of greenness. But the image on the left is 2005. And those little polygons are polygons from CRISP field plots where there's field data 4 levels of hemlock decline. And you can clearly see that in 2005, both of these stands were fairly healthy, but by 2015, that top stand has gone from sort of a darkening to a lighter yellow, which is indicating that that stand is declining, while the other stand on the bottom has sort of maintained its greenness. Now, again, we expect to see some interannual variation, but if we're comparing these two hemlock stands to one another, if there was some prevailing climate condition, we would expect them both to experience the same thing. But this fits in really nicely with the field observations of hemlock decline related to the woolly adelgid. Similarly, here's a map showing a change in greenness. So we can use this change in greenness over time to get an idea for where we might have declining stands of hemlock. And so the image on the bottom left there is showing a hemlock stand that is that hasn't changed very much, so it's still a fairly healthy hemlock stand. This corresponds to what the field data suggests, whereas the plot on the right, which corresponds to this blue dot on the top here, that darker red shows a larger decline in greenness and indicating a greater extent of decline in health. All right, so this is all really just getting started. We're scratching the surface here. And so moving forward, our plan is to continue using some of the CRISP field plot data as training data for the remote sensing algorithms that Kelsey is developing to map the distribution of hemlock stands, but also quantify changes in health over time. Once that is all in place, we'll apply this algorithm to the Catskills within the blue line. And then once we're allowed to kind of get outside and be near people again, we will get out and do more ground truthing of some of the places that we've identified at different levels of decline using the remote sensing algorithms. And then we'll plan to bridge the Catskill mapping project with the invasive species mapping project that we're working on for DEC regions 2 and 3. And through all of this, we hope that we can not just build these maps, but use them to learn more about sort of the temporal and spatial patterns in hemlock woolly adelgid related hemlock decline. And one of the other things that I'm really interested in exploring is using, there's some new satellites, you could do this with Landsat as well, that have a thermal band on them. And so they can quantify the temperature at the surface of the earth or at the surface of a forest canopy. And this is a great opportunity to better understand how a forest thermal properties might change as hemlocks start to decline. So, you know, we all know that hemlocks are important for maintaining water quality and keeping temperatures cool. And so we can start to see how at least the surface temperatures are changing over time as the hemlocks are declining. So before I open this up to questions, I need to thank the collaborators on these projects. So Kelsey, I mentioned, Rich Hallett at the Forest Service, Jason Smith, who's at the New York Restoration Project, and Clara Pregitzer at the Natural Areas Conservancy. And so I'd love to have discussion for whatever time we have left, and also feel free to shoot me any emails with any additional questions.
Great, that's excellent. Thank you, Andy. We do have some questions. We do have a question in the question and answer box, if you can see that.
Let me,
there's one from, I can read it to you. It's from Kate O'Connor. Are you factoring in elongate hemlock scale and other stressors into these apparent declines?
Yeah, so no, no is the quick answer. We can't really distinguish the drivers of defoliation using remote sensing. But two quick thoughts on that. First, if you're familiar with Dave Orwig's work, he's at Harvard Forest. He's been doing a lot of research exploring hemlock decline. His sense is that the elongate scale seems to, in some ways, benefit the hemlock when faced with an adelgid outbreak. And the reasoning behind that is it reduces sort of the nutritional quality of the needles, which makes them a poorer food source for the adelgid, which in turn can maybe slow the rate of hemlock decline. But to the extent that there's field data that might provide more information about the prevalence of elongate scale versus adelgid, we may be able to say something about that using the remote sensing if there's maybe some sort of distinctly different patterns in decline in the trees, like temporal patterns in declines of the trees over time, then maybe we can sort of get at that. But beyond that sort of information, I think it'd be really difficult to factor in those other stressors. But that's, I mean, that's a great question. And I sort of view remote sensing as a way to kind of get broad scale information that we can't get on the ground, but there's a whole lot of questions that are really difficult to answer using remote sensing. Is the role for CRISP partners to aid in the ground truthing? So my understanding of the funding agreement is no. So if anyone wants to, I think we'd be more than happy to have the help. In my conversations with John, what we talked about is maybe Kelsey and I coming up and going to some plots with him to do some ground truthing, or providing us with some locations that we might be able to check, and maybe for Chris providing us with some data that we can incorporate into our work. But I don't think, and John, let me know if I'm wrong, I don't think there's any sort of formal role that CRISP is supposed to play here.
Well, I think that my answer to Meredith's question would be yes, and that there are a number of partners that could give us access to properties or give you access for your ground truthing, and that would be something that you're probably going to need depending on which sites you want to visit outside of the ones that we're monitoring in CRISP.
Right, but there's no like mandated role for CRISP to play, right? I guess that's what I was sort of getting
right at. Yeah, I think it's a volunteer helpful role, if that makes sense.
And we would love to have that volunteer help
Yes.
as we go through this, especially you know, with what's going on now with COVID. It's not clear to us when we're going to actually be able to get out and do field work, and the lack of ground truthing will make some of the other work that we're trying to do here a little bit more difficult. Thanks, Brian. That's great. I will certainly do that. Other questions or thoughts about how maybe the products that come out of this can be used can be more useful to maybe practitioners? Yeah, having foresters check areas could be great. Maybe one thing that we can do, maybe we can have a smaller sub-meeting at some point, and we can provide some GPS points of places that we'd like to check, or even the inverse of that. If there's foresters that know of certain stands that are in different stages of decline and they have GPS points they can give us, then we can work that way as well. That's great.
Andy, do you have any sense of, there's a lot of different factors that go into this, like density of hemlocks and hemlock canopy, but how much change you would need to see in the hemlock canopy, how much you could detect? What's like the minimum amount of decline you could detect with this methodology?
That's a really good question. I'm not sure yet. Yeah, so if it were a canopy that was pure hemlock, that will probably give us those will be the stands where we will have the highest sensitivity, because we won't have to worry about variations associated with other species. I think what we would have to do is look at some of the healthy stands and figure out, okay, well, what's the normal interannual variability and sort of greenness of the canopy? And we probably wouldn't be able to detect anything except for what was outside of that normal range. That said, another approach that we can take is we can compare the year-to-year variability of one stand to maybe like what the mean change is for other stands around it. And if you start to find stands that are all of a sudden behaving differently than kind of everybody else, that can be another way to, with a little bit finer sensitivity, start to tease this out. But I don't know if it's like, a 10% decline in foliage, or does it need to be like a 25% decline? I'm not sure about that yet. Yeah, so Chris is pointing out we could use the average hemlock stands to train the model. Yeah, that's a great idea. And Rich Hallett, who's our collaborator on this, he worked with Jennifer Pontius quite closely on that work. And so we can overlay and have planned to overlay some of those data for those particular years with the Landsat data as additional sort of ways to do the training. That's great. How much we're looking at soil type. For the scope of this project, I should point out that we're supposed to complete this project by December. So the scope of what we can do, at least for this sort of first phase, is going to be relatively small. But soil types can certainly help us to better refine where we think a conifer forest is a hemlock forest. And the other thing that we can start to do when we have these really broad extensive spatial data, we can start to look at are there patterns where certain soil types that hemlocks are growing on are declining faster or slower than hemlocks on other soil types. So we could start asking some of those questions, and I suspect that once at least this phase of the work is done and Kelsey keeps working to turn this into one of the chapters of her dissertation, she will start to explore some of those questions as well.
We have some more questions in the chat box.
Oh, yep.
And suggestions. Gary Levitt has says that the ground truthing from our Dries et al. 2004 study may be useful.
Yeah, so this is great. It'd be great to start compiling, I guess, a list of sort of known ground truth data that we can incorporate into this. And the nice thing about Landsat is these data can be as old as like 30-something years at this point for us to be able to use them. So thanks, Gary. I'll check that out.
And then Kelsey has a question. Down.
Yeah, right. So to the extent that we can either get out or leverage DEC foresters to, in the field, maybe map out different stands of white pine versus hemlock, we might be able to do that. Even in Google Earth imagery, white pine is pretty easy. I shouldn't say pretty easy. It's fairly easy to tease apart from hemlock. So we may even be able to outline a few stands in Google Earth and pair that spatial information with some of the satellite data to see if we can start to tease those apart. And oh, that's great. You work with oak wilt. Yeah, so we should talk further because there aren't too many examples of oak wilt in New York that are at least at our large enough spatial scale where we can start to see if we can see it from satellites. Yeah, as you point out, most are single tree infections. But if the canopy of that tree is large enough, or there's a couple of trees in a location, we may be able to use that. There's also an experiment at Black Rock Forest where they did sort of some girdling of oaks to sort of mimic what they expect will happen with oak wilt, and those plots are big enough for us to see with satellites. So we were thinking about using those as sort of a first pass for, can we sort of detect these things? What does it look like compared to, let's say, a gypsy moth outbreak or something like that? But yeah, Kelsey, that would be great if we can chat about this at another point. So we have not yet developed the ground truthing protocol. So like I mentioned, we're about a couple of weeks into this project. So once Kelsey is done with classes for the semester, we can really jump in full steam and start to think about that. And so maybe the thing to do is for us to figure out exactly what the ground truthing needs will be and what that looks like. And maybe through John, if you don't mind, we can try and organize for all of you who might be interested or want to help or contribute in some way. We can organize some other kind of sub-meeting via Zoom at some point and talk about all these things and how best to approach it and maximize the amount of data that we can get.
Yeah, that sounds like a great idea.
Yeah, I'm like very positively overwhelmed at all the contributions that are potentially out there. This is great. I think it'll make the work that we're doing a lot better and hopefully a lot more useful.
Does anyone else have any questions? I would just say, Andy, I think this is a great project. I'm really happy that you're doing it and using Landsat imagery and the worldview imagery together. I think it's great concept to try, and it'll be great if we can, on a wider scale, monitor our hemlocks, which was our original concern.
Yeah, I think this will be really exciting. And, between some of the early work that Kelsey's done, as well as the Avarice work and some of that earlier work I showed from New Jersey, it seems like it's pretty promising that we'll be able to do this. It may not be exactly with the level of sensitivity or spatial resolution that everyone will want, but I think it will be a good way to start pointing out, hey, here are some forests that are in decline. Maybe those are some places to maybe target drone flights or target some additional field observations, which will hopefully make the whole sort of mapping and management process run more efficiently.
And we got people are offering to help. Mark Wolf at Mount Top Arboretum. They have mapping of pure hemlock stands versus hemlock spruce forests, and Meredith Taylor has data sets for forest stand information that they're offering. So that's great.
Yeah, this is wonderful. Thank you all for listening and for offering up to help and provide data sets.
Yeah, we'll probably need to end it there. I really appreciate you giving this presentation, and it's a really exciting project, and it has implications that could help us here in the Catskills and throughout New York State. So I'm really excited that you're working on this project, and thank you for the presentation, Andy.
Us too. Thanks for having me. This was really wonderful. Thank you all, and it was nice meeting everybody remotely.
Thanks. So to continue with the CRISP updates, I want to thank my colleague Dan Snyder, our field projects manager. He's added quite a bit of information to the CRISP website, which is www.catskillinvasives.com. Dan's added our upcoming remote programs in our events section to our website. He's added updates, or under the update section, we posted a summary of the who's doing what in invasive species management in the Catskills and fact sheets for the species found along the Ashokan Rail Trail. We were working with stakeholders to develop a Ashokan Rail Trail invasive species management plan. We're putting that on hold for now. We've also been sharing information as a resource on Facebook at Catskill Invasives, and we're on Twitter at CRISP News, CRISP_news. So we're putting more content out on social media, putting more out on our website to be a resource there for you, so that you can know what's going on here in the Catskills. And there are a lot of webinars that are happening that I have up on the slide here. I also want to mention that Dan Snyder's been out mapping lesser celandine along the Sawkill Creek in Woodstock. Lesser celandine is an early detection rapid response species. We've been posting about it on social media. It's one that you should become familiar to how to identify and report an IMAP invasives if you see it. We are finding more and more of that in certain areas of the Catskills. So it would be great if we had a better sense of where it was. So for partner updates, I wanted to just say that some organizations have some of their field staff out in the field working under certain safety precautions due to COVID-19. And one thing that people should keep in mind is that if you want to reach staff that you've worked with in the past at some of our different partner organizations. Probably emailing them might be the best way for most people, in that they have access to email and they may not have access to their phones, other methods of communication. But for some organizations, you may want to try to reach out to several people in that organization to get a response, because with most of us working from home, all of us are dealing with different challenges. So on the slide here, I posted some upcoming events that people sent in, some that we knew about, some that we stole from websites that we saw were coming up. We'll be posting them on our CRISP website, catskillinvasives.com, so you could get access to these links there, if that's easier than going over them now. But Cornell Cooperative Extension in Ulster has an online spotted lanternfly workshop that's coming up on May 13th at 9:30. Cornell Cooperative Extension Columbia Green on April 25th at 10 is supporting wildlife and adding beauty with native trees and shrubs. And CC Columbia Green is working with the Nature Conservancy on May 5th at 1 p.m. There's a webinar, Keep Forests Healthy, a tool to assess resilience, health, and productivity. That webinar highlights the Keep Forests Healthy assessment and scorecard. That's a tool to help landowners identify risks and strengths to the long-term health of their woodlands. They'll explore what makes a healthy forest and how to assess that in your woods. To do this, you'll learn key concepts and share the Keep Forests Healthy assessment and scorecard. This is a great tool for landowners, stewards, and forest professionals. So that's one that you want to keep in mind to tune into coming up in a few weeks. IMAP Invasives, they have under their training section of their website some trainings coming up, including the IMAP Invasives mobile app training on May 13th at 1 p.m. One thing that I've been doing since we've been in isolation here at home is walking around my neighborhood and using IMAP Invasives to map some of the invasive plants and animals around my neighborhood. So it's a tool that I hope that people will continue to use, that more people will learn how to use, because that's a database that we're using to know where invasives are in our region and to use that information to figure out what to do about them. The Otsego County Conservation Association, I have their calendar link up on the slide. They have a couple events tomorrow. April 22nd is Earth Day. There's a webinar, The Bigger Picture, and at 2 to 3 p.m. tomorrow is the Digital Earth Festival webinar, Gardening in a Warming World. And to move on to the next slide, we have our monthly PRISM webcast coming up next week on April 29th. That's at 11 on the last Wednesday of every month. We will be there to give updates along with the other PRISM leaders. So the next section that we have is NASMA on their website. They have a webinar that's tomorrow at 1, Meet the New EdMaps 1, One Platform, One Continent, Improved API on April 29th at 1 o'clock. They have Eyes in the Sky, leveraging new remote sensing technologies to detect invasion at a distance. And just a reminder that the National Invasive Species Awareness Week is May 16th through 23rd. That will focus on local events and awareness. And please remember that the New York State Invasive Species Awareness Week is coming up on June 7th through the 13th. The theme is focused on invasive species. Probably most of that is going to be remote, and we're looking for ideas and partners that want to collaborate. with one thing I would mention with or keep in mind with these remote webinars and programs that we're doing is that we can share them more widely. You don't have to just be in the Catskills to participate in our programs, but you could be anywhere, and as long as you have an internet connection. And I'll mention that the Catskill Ecological Research and Monitoring 2020 conference is going to be October 27th through 29th at the Full Moon Resort in Big Indian. They're planning for an in-person conference. Hopefully by then we can be together as people and meet and get to network in person at that conference. I want to remind our CRISP steering committee that we'll have our steering committee meeting at 1 p.m. today. And just want to mention that I'm not sure if you saw all the links here, but we'll post these links on our website, catskillinvasives.com. And with that, I'll say thank you, Andy, for that great presentation. That was wonderful. It's a great project, and I'm really excited about working with you and Kelsey on it. And I'll thank everyone else for joining us. Please stay home, stay safe, and stay connected so that we can keep working on invasive species and moving forward on invasive species management in the Catskills. With that, have a nice day, everyone. I appreciate you being here.